Good evening. Good evening once again. Now let us continue with the same videos. Let me select the PPT. Yeah. Okay. Now, once again, work energy theorem. We are using the same one. And this time, what you observe here is this. So work done due to a non-uniform force. Okay. Non-uniform force, we had been working out for a very longer time. Where did we work? See, we worked out here. I'll show you. In the previous one, what did I give you? I gave you something like S equal to some function of t, and thereby I found out what was the force here. The force here was nothing but 60 minus 2. Is this a constant force? No, it's not a constant force. It's a variable force. Okay. So what was the question here? Work done due to a non-uniform force. Okay. So in MWEP6, in MWEP, I think I did it for 5 also. Okay, let us see. For 5, what did we do? I gave an expression like this: A equal to k square x, or F is equal to m k square x. Okay. In MWEP5, we have written F is equal to m into A, which is nothing but m k square x. That's what we had got there. And the fourth video also, in the fourth video, we didn't get it. Okay, I will write it down. It's better. Okay, to get a comparison. MWEP4, we got F is equal to MA, and this was seen to be MK square. And in the sixth video, the previous video, yesterday's video, I had written MWEP6, F was equal to M into A, which should now be equal to, what was the equation we got? We got an equation 60 minus 2. M into 6t minus 2. Now you see, the force is proportional to displacement, force is proportional to time also. Both the things we are given. Okay. So this one corresponds to constant force. This one corresponds to force that is proportional to displacement. And this one proportional to force that is proportional to time. Okay. So if a graph like this is given and an equation for this is given, okay, don't worry and say that, okay, I have not been provided with displacement and how do I proceed? Okay, you need not worry since this is already given. That means one step you have already come across here, and you can easily solve such kinds of problems by at least by 2 methods. The first one is by work energy theorem. The second one is by making use of which one? The integration method. Now let us solve one such problem. See, I do not know. Yes. Okay. You might have a question. If something like this is given, okay, let us start with this. I do not know how it is varying. So I only know that the force F is given by m into x. So I'll put the value of k also 1, m into x. Or maybe I'll write F is equal to 2x instead of this. F equal to 2x. This should be fine. Okay, force is directly proportional to k. It is proportional to x. No. I use something complex here. Why 2x? Let me make it more complex. Let me make this as x square minus 1. Okay, x minus 1 into x plus 1. This is quite easier. Okay, let us do something like this. F equal to x square minus 1. And the question asked is, what is the work done? Okay, and again, I'll assume the same thing when the particle is moved from x equal to 0 to x equal to b. Okay, I like this b. Okay, anyway. So, and I want to find out the work done. So how do we do it? Now towards it. Now we know it's a variable. Equation of motion cannot be employed. So what you need to have is, you can do it only by 2 methods. The first method is work energy theorem. The second method is by integration. Let us see whether we can do it by work energy theorem. What does work energy theorem states? Work done is equal to difference in kinetic energies. Okay. But here force is given. No velocity is given. So what should I do? Now I will write F is equal to m into A, which should be equal to x square minus 1. Okay. Or A and m is equal to 1 kg. So acceleration should be equal to x square minus 1 itself. putting m equal to 1. Now I want to get velocity. How do I get velocity from here? Velocity is not so easy to get from here directly. Okay, so there is no equation. You need to integrate this. There's no other way of doing it. Okay, so towards it, how do I integrate? Integrate is nothing but, so I will write dv by dt is equal to x square minus 1. See, here it is variable is t and here it is x square. Impossible to do it. So what should I do? Let me use the chain rule. What is the chain rule? Chain rule tells me dv by dx into dx by dt is equal to x square minus 1. I can write something like this. And this, now dv by dx, what is dv by dx? Okay, dv by dx is also not known. This dx by dt is nothing but velocity. Let me write it down here. So this should be dv by dx into dx by dt is velocity. This should be equal to x square minus 1. See, in integration, what happens is, especially calculus parts, okay, you might not get the clue until unless you say, okay, I am done with it and I do not know further to proceed. When I started here, I did not know what to do. Then what I did was, okay, when I wrote this chain rule, I have got it. Then finally, I have come at this equation. Now you get a clue here. The clue here is that I can now write this as v dv is equal to x square minus 1 into dx. Okay. So, and I said that the particle starts from rest at x equal to 0 and goes to x equal to b. When I say it starts from rest, now you see the variables here are separated. These variables are separated here. Now we need to integrate this. Okay. How do I integrate? Put an integral sign on both the sides. That's it. Nothing else. Nothing special. You need not run for 100 kilometers, right? You're not running a marathon. Integration is put an integral symbol here. Then what you do is you need to put the limits over here. So how do you put limits? In the earlier problems, I gave you the limits, but now you need to put the limits. Now, I said that when the particle started at x equal to 0, lower limit should always be the first value. Okay, what was the velocity? It started from rest. So put 0 here. When the particle reached the point B, its velocity is v. Put it v here. So it is at b here. Okay, where are the limits now? Now let us integrate this. Integrating this, you get v square by 2 limits 0 to v is equal to, now here what will happen? This will be x cube divided by 3 minus x and limits will be 0 to b. Right? Just a moment, let me pull these two to the top. Okay. And now apply the limits. Apply the limits. What do you get? V square by 2 is equal to b cube. B, I'll substitute for x. So I'll get this as b cube by 3 minus b. Okay. So thus I can now write v square is equal to 2 times b cube by 3 minus b. Now what is this v square? V square is nothing but the velocity at this point, where at x equal to b, which means which is your final velocity. So I can write this as v final square equal to so much. What is my initial velocity square? What is my initial velocity square? Vi. What is Vi? Vi is 0 because it started from rest. Now apply your work energy theorem. What does work energy theorem say? Work energy theorem tells you that this should now be equal to half m Vf square minus Vi square, which should now be equal to half into m is 1 kg. So I put it 1 here. Vf square. What is Vf square? 2 into b cube by 3 minus b minus 0. What is minus 0? Vi square. Okay. I put this value Vi equal to 0 because at x equal to 0, the particle started from rest. Okay. So therefore, now this 2 and this 2 goes away. So I am left out with b cube by 3 minus b. This is your work done. Okay. I can also write this as b by 3 into b square minus 3. Right? Yeah, b square minus 3 joules. Okay. So thus I am now able to find out what is the work done. If the value of b is given, that means it starts from x equal to 0 or moves a distance of 5 meters. I can substitute this value and get the value of the work. Okay. So I hope you have understood this method. Now I have not shown you the second method. We have only done by the first method. Which method is this? Work energy theorem. Even here also, you needed some amount of integration. Let me do the second method also. Just give Okay. So now I have got this by work energy method. Now I want to get this by another method also, because the entire course is only related to how do I get, okay, by the same answer by more than one method. What is the second method now? Second method would be M2 is by calculus approach. Calculus approach. Hey, what special calculus here? Okay, let us find out what is the force. What did I take force as? The force is x square minus 1. Okay, the force is x square minus 1. I will write it here. X square minus 1. Now, what is work done according to calculus? Integral of 0 to b of x square minus 1 into dx. Okay, why is it so? Because I just substitute the value of f4 here and I got this. So which will now be written as 0 to b. Okay, I'll not write 0 to b. Let me integrate this x cubed by 3 minus x 0 to b, which would now be again b cubed by 3 minus b, which would be equal to b by 3 into b square minus 3 joules. Yeah, see how fast we have come. In M1 first method, you see, I started from here, kept on going like this and came here. Okay. In the second method, I did it in 1 second. In 1 minute. Within 1 minute, I was able to do. So sometimes work energy power method, work energy theorem might be a bit complicated. Sometimes calculus would be very, very easy. Okay. It depends upon the problem. And there's no hard and short code rule saying that, okay, we can always do every problem by work energy theorem. Okay. So keep this in mind, depends upon the context of the problem. So it is not that every time you can do the same method. Okay. So with this, let me stop here, and you can also try exploring in a similar way. Maybe you can try it out as a homework and you can mention to me, instead of taking f equal to x square minus 1, if I had taken f equal to t square minus 1, function, the force dependent on time. Okay. Then what kind of problems would you have encountered and which method would have been easier for you? Thank you friends for watching this video, and do like, share and subscribe to my channel, okay, for further updates, so that, okay, so you can also, so this video can be shared by others and they can have a look at it. Thank you friends for watching. Just a minute. Okay, so let me stop here. In the next video, let us see some. Okay, thank you.